Bismillahirrahmanirrahim. Today we are going to start the 10th lecture of Discrete Structures CSC 102. In previous lecture we have discussed divisors, prime numbers, and we have discussed also the fundamental theorem of arithmetic. We have studied also the division algorithm, how we divide the numbers, what is quotient, what is the remainder, and we have also studied greatest common divisor, which is called GCD, and least common multiple, LCM and GCD. You have studied already in earlier classes. And at the end we have studied what is the relative prime numbers whose GCD is 1. Actually they are, the numbers are called relatively prime. So today we are discussing what is a rational number and their properties, what is irrational number, what are the absolute values of a number. We'll prove the triangular inequality for any two numbers, and we will discuss floor and ceiling functions. So what is a rational number? I hope you all know what is an integer. Integers are 1 plus minus 1 plus minus 2 plus minus 3 and so on, which include also the 0. This is a set of integer which is usually denoted by z. You have studied earlier this. Now what is a rational number? A real number, basically it is a real number also. Any real number R is called rational if and only if R can be written as quotient of two integers. For example, as we can see here, R can be written as A divided by B, where A and B must be some integers, and there is another condition on B, that B must be non-zero. If B is 0, you know any number over 0 becomes undefined in mathematics. So for R to be a rational number, R can be, or R must be written in the form of a quotient of two integers A and B, where B must be non-null. A real number that is not rational, any real number which cannot be expressed as a quotient of two integers A and B, that is called irrational number, or you can say that reverse of a rational number, a number which is not rational is called irrational. More formally, the definition of rational number is given here. R is a rational number. Here you can see this symbol denotes, we have studied in logic what it means. It means if and only if there exist integers A and B such that R is equal to AB and B is non-zero. So this is a formal definition of rational number. Now we see some numbers and we will find whether these numbers are rational or not. For example, we have a number 10 over 3, 10 by 3. What is this? 10 by 3. So this is a rational number. Why? Because 10 is integer, 3 is integer, and 3 is also not 0. So we are given a number which is written in the form of a quotient of two integers, where the denominator, the number which is below, is not 0. So this is a rational number. Another number in the case of B, minus 5 by 39. So this can be written as minus 5 by 39. So minus 5 is an integer, and 39 is an integer, and this number is written in the form of quotient of two integers, So this is a rational number because the denominator, the number below this this number which is below in this quotient, is non-zero, therefore this is a rational number. Now in part C you can see that this number is actually 2 by 0. Now the first condition of the definition of rational number is satisfied because in numerator the upper number and the lower number 0 both are integer. But the second condition which is imposed in the definition of rational number, which is b, the denominator must not be 0, this condition is not satisfied, so this number is not a rational number. Now in case of d, whether this number is a rational number or not, how we can recognize it, how we can find or know that this number is a rational or not. You have studied in earlier classes that if we have a decimal number just like this, and after the decimal the numbers are repeating, as we can say that the sequence 1 2, this is repeating 1 2 1 2 1 2 1 2. So such decimal numbers in which a set of integers or set of numbers repeats, here 1 2 repeats, 1 2 repeats, 1 2 repeats, so such numbers are also rational numbers. How we can prove it, or how we can see whether this number satisfy both the conditions which are imposed in the definition of rational number, that this number must be the quotient of two integers a and b, and the number in the denominator b must not be 0. So to verify that this number, decimal number, satisfy both these conditions, we can proceed as given in the part this. So we suppose that let x is this number. Here we have supposed that x is 0.12121212 and so on. So if we multiply both sides by 100, then what happens? 100x is equal to, here we have 12.12121212 so on, because if we multiply here by 100, then the decimal goes to the right up to 2 by decimal, because here we have 2 zeros. So we obtain 100x is equal to 12.1212. Now x is equal to 0.1212 so on, and 100x is equal to 12.1212 so on. We subtract 100x x from 100x here, and we subtract 12.1212 so on from this, from the right hand side of this equation, or we take the subtraction of these two equations and we obtain 12.1212 so on minus 0.1212 and so on. So if we subtract 0.1212 from this 12.1212 so on, we get what? We get 12. So here 100x minus x becomes 99x, so 99x is equal to 12x. So we obtain 99x is equal to 12, and we can divide 99 on both sides and we get x is equal to 12 by 99. So the number 0.1212 so on, this can be written as x is equal to 12 by 99. So now we can see that this number 0.1212 and so on, this can be written as x is equal to 12 by 99. So now we can check the two conditions which are imposed in the definition of rational numbers, because the numerator and the denominator are both integers, and the denominator, the lower number, is not equal to 0. Therefore this number, which is the 0.1212 so on, this is a rational number. we can do this only when the sequence of number this in the decimal number repeats, as here 0.1 to 1 to so on, 1 2 repeats. So such numbers in which any particular sequence or pair of numbers repeats, such type of numbers are also rational numbers, and we can convert these numbers into the usual quotient form of the rational numbers 12 by 99, as we have transformed this number. So the numbers in which this sequence do not repeats, for example, we have 0.12398421169. So in this we can see that there is no repeating sequence, so such type of numbers are not rational numbers. So the only numbers in the decimal form in which a sequence of number repeats are rational numbers, and in which after the decimal the numbers do not repeat are not rational numbers. So I hope you understand what is the rational number. Now we proceed to the properties of rational number. The first property or theorem or proposition is that every integer is a rational number. So how can we say that every integer is a rational number? What is an integer? Integer are basically, the set of integer is z, which is the set of 0 plus minus 1 plus minus 2 plus minus 3 plus minus 4 and so on. This is the set of integers. I hope you already know this set. Now we have to prove that every integer is a rational number. So we can take any arbitrary integer, for example, for all n belongs to z, where n is any integer, any, it could be plus 1, minus 1, plus 9, anything, 11, 100, 200, 530, it could be any integer. Now we can write any integer n as n by 1. So any integer n can be written as n by 1. So we can now this integer n, which is written in the form of n over n 1, this satisfy both the condition of rational number. For example, in the numerator we have any integer, in the denominator we have any integer, and the in denominator number is not 0, therefore n is a rational number. So this is how we can say that every integer is a rational number. So as in particular, we can take particular examples. For example, 3 is written as 3 over 1. So 3 is a rational number because it can be written as 3 over 1, where 3 and 1 are both integers, and in the denominator we have non-zero number, non-zero integer, so 3 is a rational number. So similarly we can say that every integer is a rational number. So this theorem is basically proved. Obviously it is sufficient to write these three these steps, and at the end we say that therefore every integer is rational. So this theorem or this statement has been proved. We consider another example of this. We want to prove now in this theorem that sum of any two rational number is a rational number. Now this we have to prove if we add up, if we sum up two rational numbers which are any rational numbers, then the resulting number must also be a rational number. So how we prove it? First of all, we suppose that we have two rational numbers. Suppose R and S are rational numbers. We have supposed it because the sum of two rational numbers must be proved a rational, or this is what we have to prove. So to take a sum, we must already have two rational numbers. So we suppose that R and S are rational numbers. Then by definition of rational, this R can be written as A divided by B and S can be written as C divided by D, where A, B, C, D are any integers and the denominator of in the rational number must not be 0. So here the denominator is B, here the denominator is D. So B must be non-zero and D is also not equal to 0. Now we have two rational numbers. So we have to prove that sum of these two rational numbers must be a rational number. What we do, we take the sum of R and S. So R, what is R? A over B. What is S? We can write C over D instead of S. So if we take up LCM here, how we add up two rational numbers, how we add two numbers which are in quotient form. We take up the LCM of the numbers which are in denominator, and I hope you know the how we add up these two quotient numbers. We take the LCM BD. Here we have AD plus BC, so this whole divided by BD. Now we have to investigate whether this number is rational or not. Now in the denominator we must have an integer, and in numerator we must also have an integer by the definition of rational number, and the number in denominator must not be 0. So we have to prove that the numerator is integer, denominator is integer, and denominator is not equal to 0. This is what we have to prove. That will conclude that this whole integer is a rational. So we suppose we let that P is equal to AD plus BC and Q is equal to B into D. So this number now can be written as P by Q. Now this is sufficient to prove that P is integer, Q is integer, and Q is not equal to 0. Now P is basically AD plus BC, where A is integer, D is integer. So if we have two integers, then product of two integers is also an integer, and B is integer, C is integer, and product of two integers is also integer. We know that. And we also know that sum of two integers is again an integer. So this P is an integer. Why? Because it is a sum of products of integers. So P is an integer, and BD, as we know, that is also the integers. So product of BD is also an integer. So Q is also an integer. So first condition of the rational numbers is satisfied here, that P is integer and Q is integer. And we know that B is different from 0 and D is also different from 0. That is, B is not equal to 0, D is not equal to 0 if we have two non-zero numbers. For example, 2 and 5. These two are both non-zero, and the product of two non-zero must also be a non-zero. So if B and D are two integers which are not equal to 0, then their product is also an integer which is not 0. So we can conclude that Q is also not equal to 0. So this is what we have to prove for an integer, for a quotient form to be a rational number. So R plus S, which we have written R plus S, is P over Q. So P over Q is a rational number. Therefore and r plus s is equal to p over q. Therefore r plus s is also a rational number. So this is what we have to prove in this theorem: the sum of any two rational number is rational. So we have proved the statement, and now we proceed to the next theorem. So the next theorem is the double of a rational number is rational. Now we prove that if we multiply a rational number by 2, the double of rational number, what does it mean? It means if we multiply a rational number, any rational number, by 2, then it remains rational. So we can take the help of the previous theorem which we have proved in the previous slide. So to prove a double of rational number is rational, we must have a rational number. So we suppose that r is any rational number. Here we multiply r by 2. Now we can write it as r plus r. So what we have proved in the previous theorem, that sum of two rational numbers is a rational number. So r is a rational number, r is a rational number. It could be, these numbers could be same. So r plus r is a rational number because it is a sum of two rational numbers. So if the right hand side is a rational number, then the left hand side must also be the same as rational number. So we can conclude here that the double of a rational number is also a rational number. So I hope you understand this, how we can conclude it that the double of rational is rational. So we proceed to the irrational numbers. Basically a number which is not rational is irrational number. So such type of numbers you see very oftenly in mathematics. For example, square root of 2, square root of 3, pi, these are all irrational numbers. And how these numbers arise in geometry or mathematics, we will see in the next slide. So I have told you in rational numbers that if in a decimal form, if after the decimal any sequence of number which doesn't repeat, here no number, there is no sequence after point 4 1 4 2 1 3 5 6 2 3 7 3 0 9, there is no sequence which is repeating in this number after the decimal. So this number is not a rational number. We have proved earlier that a number in which some set of numbers after decimal repeats, that can be converted into a quotient form p over q, which will be then the rational number. So such numbers such as square root of 2 is basically 1.4.4142 and so on. Such numbers are irrational numbers. These numbers cannot be written in the form of p over q. Again, the under root 3 is also an irrational number. Pi is, the value of pi is 3.1214. I don't know exact value of pi, but this is approximately like this. But after the decimal, the numbers do not repeat. So pi is also a irrational number. And there's a note that product of two irrational number is not necessarily irrational. For example, if we take square root of 2 into square root of 2, this becomes basically square root of 2 whole square. Now this square root and 2 cancels, we obtain 2. So product of two irrational number is not necessarily an irrational number. So this is this you should remember this, that product of two irrational number is not necessarily irrational, whereas product of two rational is necessarily a rational number. As we have proved that sum of two rational is irrational, we can easily prove on the same lines that product of two rational numbers is a rational number. It's a very easy exercise or theorem, and I left it for you to prove this statement that whether product of two rational is also irrational or not. Now, how the irrational numbers arise in mathematics or in geometry? In early classes you have studied the right angle triangles, in which one angle is 90. If we take the first triangle, which is this is a right angle triangle, we take the base 1 and the height 1. What will be the hypotenuse? What will be this side? We can obtain this side as by using the Pythagoras theorem, which is c square is equal to a square plus b square. What is a is base, and what is b? B is the height. So how we can find c? C is basically 1 square plus 1 square. Here we have c square. So what will be the c? This is obviously square root of 2. So this length is square root of 2. This is how we can find irrational numbers in mathematics or in geometry. Similarly, if we take the second right angle triangle, in which base is now square root of 2 and height is 1, what will be the hypotenuse? By using Pythagoras theorem, we can find that this hypotenuse will be square root of 3, and so on. We can go on and we find the irrational numbers in mathematics. This is how we can say that irrational numbers arise in mathematics in such type of problems. So next is the absolute number. Absolute number. Before absolute number, we should see what is the combination of irrational and rational number. Now, if we take R as a set of rational numbers, R is a set, or you can say Q. Basically, in set theory, we denote the set of rationals by Q. So Q is a set of rationals. This is a set which contains all the rationals, and QC is the set notation of irrational numbers. This set contains all the irrational numbers. So if we take the union of Q and QC, so we obtain the set of real numbers. Now the set R, this basically denoted as a set of real numbers. So set of real number is basically the union of rationals and irrational numbers, and how we can graphically express the set of real numbers you have studied already. I hope that there is a straight line. This here we have minus infinity, here we have plus infinity, here we have 0, here we have 1, here we have 2, and so on. Here we have minus 1 and minus 2, and so on. So this, what is this? This is called a real line. Basically, on this line, each number is either rational or irrational number, and if we take up the union of rational and irrational number, we shall obtain this line, which is called a real line. So in mathematics, R is basically the union of Q and QC, the union of rational and irrational. This is basically the set of real numbers. Now we move to the absolute number. Absolute number is basically a number which is always positive. That is, if the given number is negative, we multiply it by negative to make it positive. In actual, absolute value, absolute of a number, of a real number, what this function does, this basically makes that number in any case positive. So for any real number x, we take any real number x. This real number could be rational, it could be irrational. So what is the absolute value of x? So we define and denote absolute of any number by writing two lines around on the left and right hand side of that number, and this is read as absolute of x. Now how we define the absolute of x? This is defined as x when x is greater than or equal to 0, and when x is less than 0, I told you that this function basically converts the numbers into positive numbers, whether the given number is negative or positive. If the given number is positive, the absolute of that number remains same. If the given number is negative, the absolute function multiplies it by minus to convert it to the positive number. For example, if we take the absolute of 2, now 2 is positive, the absolute of 2 remains 2. There is no change. Now if we take minus 3, now what this absolute function does on minus 3, it multiplies minus 3 by minus. So this is what absolute function does. It multiplies minus 3 by minus to make it plus. So minus of minus 3, it becomes plus 3. So what is minus absolute of minus 3 is basically plus 3. For example, the examples are given in the bottom of the slide. So absolute of 5 remains 5 because 5 is a positive number, but the absolute of minus 4 by 7 is a rational number. It still is a real number. So minus absolute of minus 4 by 7 is basically minus of minus 4 by 7, and it becomes 4 by 7. Absolute of 0 is 0. So this is how we take the absolute of any number. Now there is a small result related to the absolute numbers. For all real numbers r, if we take that any real number r, basically r is greater than or equal to minus or absolute of r, and less than or equal to absolute of r. So this we are going to prove this in particular example. We can take that 3 is greater than or equal to 3 absolute minus and less than or equal to absolute value of 3. Now we can see easily that this inequality is always true. Here remember that negative sign here is outside the absolute value. It's not the inside absolute of value. Absolute will convert that negative number into positive, where the negative comes inside the absolute, not outside the absolute. This is basically minus of absolute of 3, not the absolute of minus 3. So this is basically the different thing, because minus of absolute of any number is not equal to absolute of minus of any number. This is not necessarily equal, because you are saying in this case that minus of 7 absolute is equal to 7 absolute. So this is minus 7 and this is 7. So you cannot say minus 7 is equal to 7. So remember that this negative sign is outside the absolute value. It is not inside the absolute value. So how we can prove this lemma or small result? Suppose r is any real number. We take any real number r, we divide it into cases according to the whether r is greater than or equal to 0 or r is less than 0. So if r is greater than or equal to 0, in this case, by definition of absolute, absolute of r is r, and also since r is positive, and minus of absolute of r is basically a negative number, as we have seen in here that minus of absolute of 7 is basically minus 7. So we can say that minus absolute of r is less than r, and thus basically if we have absolute of r is equal to r, we can write it absolute of r less than or equal to r, because in this case equality is true. So we can write in this case that minus absolute of r is less than or equal to r and less than or equal to absolute of r. Similarly, we can prove in the second case whether if r is less than 0, then multiplying both sides by -1 we can obtain this. And also, since r is negative number, absolute of r is positive, though absolute of r is greater than r, because r is negative. So absolute of r is always greater than r if r is negative. Thus it is also true in the case that this inequality holds. So therefore the given result can be easily proved by using the definition of absolute value of a number, of any real number. So the next is another very simple theorem which we use very frequently in mathematics and basic calculations. For any real number a, square root of a square is basically absolute of a. As we know that square of a is basically equal to minus a square, as you can see here on the slide. The number plus a and minus a are square root of a square. Means if we take square root of this, then this could be minus a and this could be plus a. So these two numbers are not equal, but here we can see that a square is equal to minus a square, because with the square we convert minus into plus. If these two numbers are same, but if we take up the square root of these two numbers, the resulting numbers a and minus a are not the same numbers. This is why we write the square root of a square is absolute of a, not the simple a. So we can read this theorem to if a is greater than or equal to 0 and if a is less than 0. We discuss two cases here. If a is greater than or equal to 0, then plus a is the non-negative square root of a square, because if a is greater than 0, then a square root is plus a, which is equal to absolute of a, because a is greater than 0. So if a is less than 0, then minus a is the non-negative square root of a square. If a is less than 0, then a square less than 0, then we take here minus a as a square root of this. Now if we take minus a is what? A is less than 0. So it's better to take the absolute value of a here, because we have multiplied minus here. What we have done here as same as we have done here in the absolute value definition. So we take here the absolute of a. So we can conclude that square root of any number, any real number, a square is equal to absolute of a. So we move further and we are now ready to prove the triangular inequality. This inequality is very important in mathematics and it has tremendous applications in mathematics. For all real numbers x and y are two arbitrary real numbers, means any real numbers. And what is the triangular inequality? That is absolute value of x plus y is less than or equal to absolute of x plus absolute of y. So what is basically this? And we can see that 10, if we take 10 and y as minus 5. So if we take up absolute of this is basically less than or equal to absolute of 10 plus absolute of minus 5. Whether this is true or not, this is true, because 10 minus 5 is 5 here. Absolute of 5 is less than or equal to absolute of 10 plus absolute of minus 5. So what is this? This is 5 less or equal to 10 plus 5. So 5 is less or equal to 15. So this is always true. Equality holds when both x and y are positive numbers. Otherwise, if one of x and y are negative, then the equality doesn't hold, and the left hand side must be less than right hand side. Now we are going to prove it mathematically by using some some mathematical relations and the definition of absolute value function. Suppose x and y are to any real numbers. Now first case is if x plus y is greater than or equal to 0, then absolute of x plus y is equal to x plus y. And we know that any number is less than or equal to its absolute value. So x is less than or equal to absolute of x, and y is less than or equal to absolute of y. So hence, therefore, x plus y absolute value is equal to x plus y, and x is less than this, y is less than this. So indirectly we can say that this is less than this. So what does it mean? That this implies x plus y absolute value is less than or equal to x absolute plus y absolute, or absolute of y. In the second case also, when we take x plus y less than 0, then x plus y absolute value can be written as minus x plus y, and minus x is less than or equal to minus x absolute value, because minus of x absolute value becomes plus x. So minus x is always less than minus absolute of x. Minus absolute of x is equal to plus x absolute of x, because if we take up minus 5 absolute or plus 5 absolute, it becomes 5. So these two are equal. So we can write minus absolute of x equal to absolute of x here. Similarly this, and this is equal to this, which is less than this, this is less than this. What we conclude? We conclude the triangular inequality. We have proved it for both cases. X plus y is greater than or equal to 0, and x plus y is less than 0. So we can conclude this result, and this is called triangular inequality. The next is floor and ceiling functions. We shall study only the definitions of floor and ceiling function here today, and in the next lecture we will study some properties of floor and ceiling functions. So now, what is the floor function? This basically, floor functions and ceiling functions have many applications in computer science. Especially these functions are used to convert the decimal numbers into the integers. So what is the floor function? It is denoted by floor of any integer x. How we denote it? We denote it by this. This is basically special type of brackets, this x and this, such type of notation it has, and this is called floor of x. And how we define it? Floor of x means that unique integer n such that x is greater than or equal to n and less than n plus 1. So why we say it a floor function? Because if we write any integer, any real number, for example 5.349, this is any integer. Now we see that what is the immediate less number of this number? The immediate less is this, and immediate greater than number of this number is 6. So this is 5.349. What is the immediate less integer of this number? We are talking about integers. What is the immediate less integer of this number, and what is the immediate greater integer than this number? If this is basically the 5 and the immediate greater number is 6, so what is the floor of this? Floor of 5.349 is basically what? 4, which is the immediate less integer of this number. This is basically called the floor of any real number. If the given number is already an integer, for example 5, then this can be written as 5 is greater than or equal to 5 and less than 6. So the floor of 5 is also 5, and the floor of, as we have seen here, 5.349, what is this? This is also 5. So the floor function basically converts the given real number to the immediate less integer of that real number. So this is basically the definition of floor function, and formally we can say that this is floor of x is that integer which is immediately less than that real number. X is less, basically n is less than or equal to x and less than n plus 1. So floor of any real number is that integer which is immediate less than that real number. And the ceiling function, basically here you can see in the figure or in the graph, that floor of x, if we are given x here and the immediate less integer is n, immediate greater integer is n plus 1, which is greater than x, then what is the floor of x? Floor of x is this number. So how we define the ceiling function? This is basically the reverse of floor function. Given any real number x, the ceiling of x denoted by this notation, which is the reverse of the floor function notation. Now the ceiling function is now this is the notation of ceiling function. If we take up the ceiling of any real number, this is basically that unique integer such that n minus 1 less than x less than or equal to n. Now this is the immediate greater integer than that real number. In the figure here, if we take x, what is the immediate less integer? Basically n minus 1. And what is the immediate greater integer? N. This is n. So the ceiling of x is basically that integer which is immediate greater integer than that real number. So this is the formal definition of floor function. Floor of x is equal to n if and only if n minus 1 is less than x less than or equal to n. So this was the definition of ceiling and floor functions. So in the next lecture we shall prove some properties of ceiling and floor functions, and we shall prove also some theorems which will be helpful in the next lectures of method of proofs. So till today we stop here and we summarize what we have studied in today's lecture. We have studied the rational number, properties of rational numbers, and we have studied some theorems related to the rational numbers. We saw also what is irrational number, and we see what is the real number. Real number is basically the union of rational and irrational numbers. We have studied absolute values of any real number. We have proved a very famous and very useful triangle inequality for any two real numbers, and we have studied also the floor and ceiling functions, the definitions of floor and ceiling functions. In the next lecture we shall discuss some properties of floor and ceiling functions, and we shall prove some theorems related to the floor and ceiling functions, and we shall also start the method of proofs. So till the next lecture, Allah Hafiz.